Suppose we have a coordinate plane. And on that coordinate plane, we have a curve. We'll call that curve f of x. What we want to do is we want to find the length of f of x from point A to point B. We want to find this length, or the arc length. Now, how can we do that? Well, we could use an approximation, because obviously we can't exactly figure out what that length is. So why don't we do Pythagorean theorem, or Pythagorean theorem? I don't know why I said it like that. However, the hypotenuse of this triangle is a terrible estimation of the length of this curve, clearly. So what can we do to make it better? Well, we could use multiple hypotenuses. Hypotenuse. We could use multiple hypotenuses. So if we use 3, we can find the length of that hypotenuse, and the length of this hypotenuse, and the length of this hypotenuse, and add up all of those lengths to get an even better approximation of the arc length. However, how can we get the best approximation? There's an even better way. Well, imagine that these points are all infinitesimally close to each other and not that big. And imagine that these segments are all infinitely small. So in order to find the arc length to find the arc length most accurately, we need to use a big amount of infinitesimally small line segments. And then we apply the same principle using finding the length of each of these segments using Pythagorean theorem. But how do we find the length of each of these using Pythagorean theorem? Well, let's take this one. Let's call the length of this dl. The length of this, the amount it moved in the x direction is dx. And the amount it moved in the y direction is dy. So in order to find dl, all we have to do is apply the Pythagorean theorem. dl squared equals dx squared plus dy squared. Now we'll simplify it. Take the square root of both sides. dl equals the square root dx squared plus dy squared. So this is the length of one infinitesimally small segment to approximate the arc length. Now, how do we add up all of these arc lengths using a formula? Well, we have learned from finding the area under a curve, that in order to accumulate infinitesimally small things, we use an integral. So we use an integral. We use the integral from the starting point A to the ending point B of dl. Now let's substitute this in for dl. Integral from A to B of the square root of dx squared plus dy squared. This accumulates all of these infinitesimally small line segments to approximate the arc length. However, this does not look like any integral we've seen before. How can we solve this? We don't know how to find dx, we don't know how to find dy, and we're missing the differential that tells us what we're differentiating with respect to. So let's solve this problem. I will factor out a dx squared. Now that leaves us with this integral from a to b, the square root of dx squared times 1 plus dy squared over dx squared. Now let's simplify that even more. Integral from a to b of the square root of 1 plus dy over dx squared, because of exponent rules, dx. Now, this gives us something we can actually solve for. dx, that's the differential we're differentiating in response to. And this is just the derivative of f of x. So this is easy enough. So, the formula for arc length, the usable formula for arc length, is the integral from a to b of the square root of 1 plus dy over dx squared dx. This formula accumulates all of the infinitesimally small line segments to approximate the arc length most accurately. This is based on Pythagorean theorem. Now, let's do an example. Let's say we have the graph for x squared, right? So, f of x equals x squared. So we want to find the arc length from 0, 0 to 3, 9. We want to find this distance, that length. So how do we do that? Well, we have the arc length formula. The integral from a to b of the square root of 1 plus dy over dx squared dx. Now let's start substituting in values. What is a? Well, a is where the arc starts, and that is 0. What is b? B is the x value where the arc ends, and that is 3. And what is dy dx? Well, dy dx equals the derivative of f of x, which equals the derivative of x squared, which is 2x. So dy dx equals 2x. Now let's plug in all those values. Arc length of f of x from 0 to 3 equals the integral from a to b of the square root of 1 plus dy dx squared dx. And what is that value? That value is, according to my calculator, 9.7471 about units. So what we just did is we calculated the length from 0 to 3 on the arc of x squared. So we took all of the little infinitesimally small pieces along that arc and added all of those together using the integral and the formula for Pythagorean theorem of every individual piece. And we accumulated all of those little lengths to get the arc length of x squared from 0 to 3. Well, what about the arc length of parametric curves? Well, we know that parametric curves are defined by t. X and y, the vertical and horizontal motion, are defined by a value t. So how do we figure out the arc length in these two with these two variables? So let's imagine what this graph might look like. Well, let's say at this point t equals a. So at this point we have the coordinates x comma a, or x of a and y of a. And let's say the graph looks something like that. And it goes to this point where t equals b. Then this point would have the coordinates x of b comma y of b. So how do we find this arc length from a to b of a parametric function? So let's say it's the same exact principle, or let's not say that. It is the same exact principle. Okay. It's the same exact principle. We want to take an infinitesimally small line segments and add up all of their lengths to get the actual length of the parametric curve. However, this is a slightly different technique because x and y are both defined by a third variable. Let's take this infinitesimally small segment right here. If this follows the same principle as the other arc length, then this should be dx. However, dx is now defined by a third variable. So dx equals dx dt, or the rate at which the function of x changes, times dt. because t is the main variable that we're differentiating with respect to. And dy is the same thing. It's the rate of change of the function of y with respect to t times dt. And this is, again, dl. So how do we find dl? Yeah, we'll go right here. How do we find dl? Well, it's the same Pythagorean theorem, except there's one difference. Instead of dx squared plus dy squared, it is now dx dt times dt squared plus it's terrible x, dy dt times dt squared. Now we take the square root of both sides, and we're left with dl equals x prime of t dt squared plus y prime of t dt squared. Now, if this follows the same principle, which I said it does, now we have to accumulate all of these values. And how do we do that? With an integral. So, what is the defining, what is the where the arc is coming from? What's coming from A? And the arc is ending at B. And we have to accumulate all of the lengths of DL. Now, so we're substituting DL in. We're accumulating all the lengths of DL. We're accumulating x prime of t dt squared. Oh shoot, I forgot the square root sign. Square root of x prime of t dt squared plus y prime of t dt squared. Now let's simplify that. We end up with the integral from a to b of the square root of x prime of t squared dt squared plus y prime of t squared dt squared. Now again, we are missing the defining differential that tells us what we're differentiating with respect to. So we got to keep integrating or keep simplifying. And we're left with, if we factor out a dt, we're left with square root of dt squared times x prime t squared plus y prime of t squared, which further simplifies into the arc length for parametric curves. Arc length parametric curves equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. And this follows the exact same principle as the original arc length formula, as it follows Pythagorean theorem. We can solve for dx dt, we can solve for dy dt, and dt is there as the guiding differential for what we're differentiating with respect to. This symbolizes the accumulation of each of these little dl's, these infinitesimally small dl's, to find the arc length with respect to the defining variable, which is t.